Hello everyone. Hope you all are doing good. And today we had weekly contest to 91 on Leetcode. It was my first Leetcode contest after a layoff of over 1 month's time due to the college semester exams, but now they are finally over. And I managed to solve the first three problems today. So let's quickly walk through the solutions real quick. And here we go. So let's start with the first problem. Calculate amount paid in taxes. So I will explain you the problem statement real quick in case you haven't read it yet. So here we are given this array brackets and each element contains two values. One is the upper limit and second is the corresponding rate. And we're also given the income. So for this given income, we need to find the total amount of tax that we need to pay. So what this precisely means, I'm just going to tell this to you. Let's consider this particular test case. So let's have this particular number line here. So we have 3, 7, 12. So these are the upper limits. So what this means is that up till the amount 3, we need to pay tax at a rate of 50%. Up till the amount 7, that means 3 to 7, we need to pay the tax at a rate of 10%. And up till the amount 12, we need to pay the tax at 25%. Right, so this is what the problem means. And we're given the income 10. That means we need to calculate the tax till the amount 10. So given the income 10, we need to determine what's the total tax we need to pay. Right. So total tax that we need to pay. So we need to reach till here. So we have the first interval 0 to 3. It has 3 values and we are paying it at 50%. So this will be 50% of 3 is going to be 1.5. Right. Then 3 to 7 we have got 4 values. We are paying it at 10%. So this is going to be how much? 0.4. And 7 to 12 we got 12 minus 7, 5 values. We are paying it at yeah, but here's a trick that we don't need to calculate, we don't need to consider this whole interval. We only need to determine the tax up till the amount 10 because 10 is the given income. So we need to consider this interval 7 to 10, not 7 to 12. So 7 to 10, we have got how many? 3 values at a rate of 25%. So that is going to be 0.75. If we add this up, 5, 6, 2, it's going to be 2.65 and it is 2.65. So yeah, so that is all we need to do in this problem. It's a simple implementation problem. We just need to implement whatever the problem is telling us to do. And we can easily do that by maintaining like 2 pointers. Like S is going to be the starting value of the interval, E is going to be the ending value of the interval. So and E minus S is going to give us the total number of the length of the range. So first we have got S and E, we have got 0 to 3, then 3 to 7. Then here, instead of having the interval, end of the interval here, we need to have it here. Because this is where we terminate, right? We don't need to go all the way till 12. So that is something that we need to handle separately. I'm showing you my code real quick. Yeah, so this is my code. So this is my starting and ending values, and we are already given the rate and everything. So yeah, so this is what I did. My ending limit is I means most of the time it's the upper value only, but in case if income is less than the upper value, that means the income itself lies in that interval, then we need to have the end value as income instead of upper. So I've taken it as minimum of upper comma income, and rest everything I've implemented it the way they have instructed me to do. So yeah, that is it for problem A. It works in order of n time and O1 space if someone asks, but here we don't need to pay too much attention to that. The constraints are it's just a simple implementation simulation problem. That is it. So we are done with problem A. Hope it all made sense. Pretty straightforward. Now let's move to problem B. Problem B is a nice problem. I enjoyed solving it during the contest. We are basically given a m cross n grid, and this grid contains values from 0 to m minus 1, mn minus 1. That means all the like permutation values, you can say, distinct values. And the thing is that yeah, let me explain the problem to you. We have a grid. Yeah, it has m rows, n columns. Right. Initially we are in the 0th row and we need to reach the last row. So objective is to travel from the 0th row to the first row to the last row. Okay. And in order to move from one row to the next row, we are allowed to make a move, and that particular move is defined by, I'm just telling it to you. It, yeah, so basically let me move on to the next page. If like, yeah, we have this matrix and say we are at this particular position, so we can either move here or here or here. Okay, so we can move to any column of our choice, but every move has a cost associated with it. So if we are suppose at I comma j and we are moving to the next row, that is I plus 1, to any column, say we are moving to the kth column. So the cost associated with this is that we're already, when we're at a particular cell aij, then that particular value has to be considered. Plus, we need to we have a cost of moving cost, and for this moving cost, we have a separate matrix. So this matrix maintains a mapping of all the values from all the distinct values, and it's corresponding, like if we are suppose we are at this particular value, say this value is 5, and we are moving to the 0th row, then the corresponding cost would be move matrix 5 comma 0. So it has got all the values in all the corresponding columns. So if we are moving from a particular value to a particular column, then this particular matrix gives us the corresponding cost. So we can easily find that particular value from that particular matrix. So it will be something called, like if we have this, yeah, move cost is the name of the matrix itself. So we can like define it in this way, that we are at this particular value aij and we are moving to k, right? So this is the moving cost. This is how it's calculated. So now for this given matrix, okay, let me do one thing. Yeah, so for this given matrix, we need to calculate the minimum cost to travel from this column, this row to this row, and we can start from any particular cell of our preference, and we can choose any destination cell of our preference. So the source cell and a destination cell is our preference. Only thing is that we need to move from the first row to the last row. It can be like this, first here, then here, then here, then here, or it can be like this, anything. But of all the possible moves, we need to determine a minimum move, the part having the minimum cost. Right. So the main thing is that it's a typical, like the way I thought of it is I solved it using dynamic programming. The what I did was I defined a DP state I comma j to be the minimum cost, yes, the minimum cost to travel, minimum cost to reach the last row when starting from the cell I comma j. So this is my dpij state. Let me again tell you what this means. So yeah, so this is a DP state. Let's like discuss the transition. So suppose this is my I8 position, this is my J8 position. Suppose I'm currently at this particular position. So minimum cost to travel to the last row when starting from I comma j. So what's the minimum cost to travel from here to the last row? This is what DP of ij is giving me. From here I have got so many options. I can either move to this or here or here or here. I want n options here. So let's say that this particular column number is represented by k. Okay, k at column. So from dp of I comma j, I'm moving to I plus 1 comma k at position. So then the transition can be defined as we are currently at a of I comma j, so this cost has to be considered plus the moving cost. So moving cost, as we discussed, that we have the move cost matrix. Let's have a bit more space, then that would be easier. Yeah, dp of I comma j, we are initially at aij position, then we are moving to move cost, we are at a of I comma j, and we're moving to the kth column, and after that the remaining part will be calculated by the dp state itself, the pre-computed dp state. So we have now moved to the I plus 1 at row and k at column. So this is the dp state, and we need to consider the minimum over all the k values, from 0 to n minus 1. I hope this made sense. The minimum cost when starting from I comma j, so the cost that we have to calculate, the cost of the cell plus the moving cost plus then the pre-computed cost by the dp that we are already like computing the bottom up way. So this is the base case. We can't move any further. So base case will have only a comma ij values, grid ij values, and in the general case we have this particular dp function, a dp state. And after that, finally, when we have computed these dp states in a bottom up way, then we can either start from here or start from here or start from here or start from here. So the answer is going to be the minimum over all the dp of 0 comma j values for all j belonging to 0 to n minus 1. So we calculated dp values in a bottom of it, the 2D dp grid that we'll have, and then this is going to be our final answer. So I hope that this logic made sense. I will quickly walk through the code so that the implementation also becomes clear. Like, it's just what I said, I've implemented it. Base case is that we are at the m minus 1 at row, where we only consider the grid cost because we can't move any down. We can't move further down from there, right? But if we are considering general case, the rows above that, so we have to consider the grid cost as well as the moving cost. And then since we are calculating it in the bottom of way, so After the rest of the part is taken care of by the pre-computed DP values itself, and over all the options we take the minimum. So yeah, this is how the solution works. I hope it made sense. It fetched me AC. If we are talking about the time and space complexity, then we are having order of O, like, yeah, let's discuss the time space complexity also. So we have a total of n cross m states, and for each state we are considering n values because we are doing this thing here. So each state we are considering all the k values from 0 to n minus 1. So this is the time complexity, and it fits well within the constraints because constraint was n and m is less than equal to 50. The cubic solution works, fits in the time constraints pretty comfortably, and space is also order of n into m since we're using a DP array. So yeah, that was it for the second problem. Now let's move to the third problem. Third problem is fair distribution of cookies. Yeah, this was a nice problem. So let me share my intuition and approach with you. So yeah, basically in this problem we are given a bag of cookies, n bags of cookies, and we have k children. So we need to distribute this bag amongst those k children in such a way such that like there is one criteria: unfairness. Unfairness is defined as the maximum cookies that one single child gets. So that particular maximum cookies has to be minimized. So it's an optimization problem. And whenever we think of optimization problem, then like there are three popular ways of solving it. Either we solve it a greedy way, or we solve it. We try out all possible options. We try to solve it in using DP, or we solve it using binary search. And this particular thing, like minimizing the maximum or maximizing the minimum, like the first thing that occurs is binary search. Like that's how I think. So I thought that okay, why not give binary search a try. So what I thought was that let's define something as fx is going to be is unfairness. Oops, sorry. Let's write it with a bit more space. Yeah. So let's define a function fx which tells us that is unfairness, total unfairness less than equal to x possible? Yes or no? It's a simple boolean yes no function. So if we like try to form a graph for this x and fx, then we'll notice that it's kind of like if it's a very large value, then it's always going to be possible because you can always have an unfairness less than equal to infinity 10 to the power 8, and so it's always going to be true, 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 and there is going to be one point when it is going to be false, right? Because there is going to be one point where the maximum number of sweets will be less than this particular value. So this basically turns out to be a monotonic a monotonic graph. So it turns out to be that our search space is monotonic in nature. In this part it is true, in this part it is false. So this particular value, which is the lowest value which is true, this is our answer. So this is the reason why binary search is applicable here. This is a search space, and in this search space we can binary search over all the options, and yeah, that is it. So now the question boils down to finding this particular value. How do we, like, given x, we need to check whether the unfairness value less than equal to x is possible or not. Let me explain this to you with a test case. Just give me a second. Yeah, let's consider a test case given in the question itself. So see this, we got k equal to 2, we have two children with us, and we have the bag of cookies with values of 8, 8, 8, 8, 10, 20, 10, 15, 20. So we got 5 bags. We need to distribute it among the two children such that the maximum number of cookies that one child gets is as low as possible. Right, so we have suppose got two of these children. So what I thought was that we can do it in a greedy way. We will keep acha, and one more thing, since the binary searching it, so we already have the particular answer with us, and we need to just check whether the answer is true or not. So that is the beauty of binary search. It simplifies. We don't have to solve it. We have to check whether the answer is correct or not. So let us check whether the answer say whether 40 is allowed or not. Can I have maximum value? Can I have accommodate at least 40 values inside or not? So what I would do is that maximum permitted value of these two children is 40. So try to assign a maximum value every time. 20, then 15 here. So we have 35. I can assign any more. And remaining I'll try to assign it here. 10 plus 8 plus 8. Right, so I try to assign a maximum value every time, but it so happens that this greedy thing does not work. This greedy approach does not work because there are cases when we can't, where like this gap cannot be filled in this particular way. So I initially tried to solve it using greedy, but it failed. So then it occurred to me that I looked over the constraints, and the constraints was wow, less than equal to 8. So then it's just brute force. I need to just consider all possible permutations. Like I have this particular thing, right? Suppose I have this values as 1, 2, 3, 4, right? And so if this is the thing, then and I have the particular answer as, say, I need to check whether x is less than say 3, it's possible or not. So I will have, okay, 1 plus 2, 3, up till here it is possible, up till here it is possible, up till here it is not possible, so I will not consider this. So we can have at least 2 children here, and if this particular value is less than equal to k, that means that we can have at most k values, then it is fine. Otherwise, that particular permutation is not possible. Like, is this making sense, or shall I describe it again? Okay. Say suppose, mm, yeah. So that's what I did here. Say suppose, yeah. Let's take a better test case to understand this. No, so what we're doing is that 1, 2, 3, 4. This is, and we are given the value x equal to 3, as I said. So, and the value of k is already predefined to us. We have two children. That means that we have to distribute at most x candies to two children. So we can distribute one child also. That's not the case, but we can't distribute it to more than one child. So this means that we have distributing at most 3 candies. So I can accommodate this and this. Well and good. Then I can accommodate this. But then I find that this is not possible. Like I require 3 children here, but I have only 2 children. So this combination does not work. Then I can have something like, if suppose x value would have been 4, say, then maybe this x value would have been suppose 5, I can say. Then 1, 2, 3, 4 will still yield me 2 plus 1, 3. Then this will not accommodate. And 3 and 4. So this will not work, but say suppose I have the permutation as 2, 3, 1, 4, then I can accommodate this only two children itself. Right, so when we have 1, 2, 3, 4, there are total 4 factorial ways. 1, 2, 3, 4, 1, 2, 4, 3, then 1, 3, 2, 4, 1, 3, 4, 2, dot, 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 4, 3, 2, 1. So one by one, we need to check for all the permutations. Like here, this required 3 children, so this exceeds the value of k less than equal to 2. But when we tried for this permutation, then this worked. That we can distribute these, if we move in this way, then we can distribute it in among 2 children. 2 plus 3, stop. 1 plus 4, 5. So likewise, since our n value is at most 8, so we can generate all the 8 factorial ways and one by one check it in O of n time. So this check function will work in order of n factorial into n time, and the total time complexity, since we are doing binary search here, just a second. Yeah, so since we are doing binary search here, yeah, so I told you we are doing binary search here, right? It's monotonic search space, and for each value of the binary search, we are checking for that particular value. So that means that our time complexity is going to be order of log of, say, my maximum value. I'm considering it as how much? 10 to the power 5 into n factorial into n. And this very well fits inside our time limit. Order of 10 to the power 5 is it's going to be less than 10. It's going to be less than 30 because 2 to the power 9 32 bits is 10 to the power 9 is 10 to the power 5, so it's something around 20 something, and this is 8 factorial into 8, so that is very much within our time constraints, so that's not going to be an issue. So that is precisely what we had to do. Let me show you my code. Like what I did was that to generate all the permutations, I used this next like first I did binary search. Like I considered that these are my starting and ending points, and I binary searched over this interval, and in order to check whether it is satisfied or not, I first like generated all the permutations and then checked whether how many number of children I need, I can distribute it amongst. And if the number of children that that are needed to be distributed is less than equal to k, then then we have found that particular permutation is valid, and we can simply say that this works. This particular value of x is valid. But if we have tried for all the permutation and we still don't find any valid permutation, that means that the given value of x is not valid. So yeah, that is how the check function is implemented. I hope that it did make sense. If not, then please feel free to drop down a comment in the comment box. So yeah, that is pretty much it from my side. I hope that um, that things were clear and you guys enjoyed the contest. So yeah, that is pretty much from my side, and see you next time. Bye bye. Adios.